Today, we're diving into a medical detective story. It's all about tackling that super common frustration, why a treatment that should work sometimes just doesn't. We're going to look at a major study that's completely changing how we fight a tiny but incredibly tough stomach bug.
You've probably been there, right? You go to the doctor, get a diagnosis, you take the medicine like you're supposed to, but nothing happens. You don't get better. It's confusing, it's discouraging. But what if I told you that a lot of the time the problem isn't you, it's the bug itself? And that is exactly what we're getting into today.
Okay, let's get into the details. The culprit in our story is a very, very common bacteria. And the big problem is that our standard ways of fighting it are, well, they're starting to fail more and more often. And this isn't just a small hiccup, it's a really big deal for public health.
So meet Helicobacter pylori, or H. pylori for short. Believe it or not, about half the world's population has this little guy hanging out in their gut. For a lot of people, it's no big deal, but for others, it can cause some really painful ulcers and even more serious stomach problems. For decades, we've had this reliable cocktail of antibiotics to get rid of it, but that's changing, and it's changing fast.
25%. Let that number sink in for a second. For about a quarter of everyone treated, the standard first-line therapy for H. pylori just doesn't work. And the main reason? Antibiotic resistance. That means for 1 in 4 people, that first round of medicine is basically destined to fail before they even swallow the first pill. So what's the solution? How can we know before starting a treatment if the drugs are actually going to work? Well, this is where the real detective work begins. Researchers have figured out a new, super high-tech way to investigate the bacteria by going straight to its source code, its DNA.
Okay, check out the difference here. The old way. Think of it like this. It's like trying to identify a criminal by seeing how they behave in different rooms. You have to capture the bacteria and then grow it in a lab, which can take weeks. But the new genomic way? That's like getting the suspect's fingerprints and running them through a global database instantly. It reads the bacteria's DNA directly, looking for the exact genetic markers that basically scream, hey, I'm resistant to this drug. It is so much faster and way more precise.
Now, to prove how powerful this new method is, researchers went big. This was not some small local study. They analyzed the complete DNA of over 1,000 H. pylori samples, and they got them from 50 different countries. This global scale is absolutely crucial because, as we're about to see, where your bacteria comes from, well, it matters a lot.
So, with all this incredible data, the researchers could finally ask the million-dollar question. Can reading a bacteria's DNA tell you with certainty whether an antibiotic is going to fail? The answer they found was, well, it was stunning.
So here's the real test, right? If the DNA test says a bacteria has a resistance gene, does it actually resist the drug in the real world? And if that gene isn't there, is the bacteria for sure going to be vulnerable? This is the ultimate test of the whole genomic method. 100%. The prediction was absolutely perfect.
So what does 100% actually mean? Well, for the 2 main antibiotics they tested, Clarithromycin and levofloxacin, the DNA test was flawless. It never got it wrong. If the test said a bacteria was resistant, it was. If the test said it wasn't. Not a single mistake. This proves that for these drugs, specific DMA mutations are the smoking gun for resistance.
Now, this perfect prediction tool allowed the researchers to build something even bigger, a global map of antibiotic resistance. And what they found is that treatment failure isn't just random, it's geographic.
First up, we have Clarithromycin. It's a real workhorse antibiotic in H. pylori treatment. But the chances of it failing depend dramatically on where in the world you and your bacteria happen to be.
I mean, just look at this difference. In Southeast Asia, more than half of all H. pylori strains have the genes to resist Clarithromycin. That means the standard treatment has a 50-50 shot of failing right from the start. Now compare that to North America, where the resistance rate is just over 8%. It's like you're dealing with 2 completely different diseases.
So you might think the pattern would be the same for other antibiotics, right? But nope. For levofloxacin, another really important drug, the global resistance map looks totally different.
Here, South Asia is the hotspot, with over 51% of strains showing resistance. But in Europe, the rate is much, much lower, around 12%. The takeaway here is crystal clear. A one-size-fits-all approach just doesn't work anymore. The best treatment in one country could easily be one of the worst in another.
Now, as with any great piece of research, it's really important to be clear about what it doesn't tell us. This study is a huge leap forward, but it's not the final word.
there are still some pretty important questions left to answer.
First off, even though it was a huge sample, there are still some parts of the world they couldn't get much data from. Second, this study totally cracked the code for clarithromycin and levofloxacin, but the genetic clues for other important antibiotics like amoxicillin and metronidazole, they're still a bit fuzzy. And finally, this is just a snapshot in time. We still need to figure out how quickly these resistance maps are changing year to year.
But let's get to the bottom line. This quote, directly from the authors of the study, is the single most important takeaway. They say using these antibiotics empirically, that's just a fancy science word for using guesswork or just going with standard practice. What they're saying is that the era of prescribing these drugs without first testing the bacteria for resistance is over. In every single region they studied, that kind of blind prescribing just isn't a good idea anymore.
And this leaves us with a really fascinating final thought. We're moving toward a world where knowing your bacteria's zip code, its unique genetic profile, and where it came from is just as important as knowing your own medical history. It's a massive step towards a future of truly personalized medicine, where we can choose the right drug for the right bug for the right person the very first time.